Continuing with Chapter 9, which, if you remember, the title is Connector, Assignment and Flow Problems. We'll be looking at assignment today. Now, you had a bit of an easy run on the last exercise, 9A. 9B is a little bit harder, a bit more work to do. 9B is actually headed up Matching and Assignment Problems. And your learning intention is, can you use digraphs? I'll explain what they are. Adjacency matrices, you met them before. Bipartite graphs, that's something new. To solve matching and assignment problems using this technique you haven't met before called the Hungarian algorithm. So one by one, make sure you understand each of these components of the unit before you move on to the next. First of all, digraphs, which actually stands for directed graphs. A directed graph is one with arrows of direction on it, as the figure on the left, A, B, C, D. There is a path from A to B and there's a path from B to A, but there is no path from C to B. On the right is an adjacency matrix, which you've met before, and so you put 0, 1 or 2 or whatever, depending on how many ways there are to get from somewhere to somewhere else. This one is not symmetrical as they were before because, as we said, there's a path from A to D, but there's no path from D to A. There's the solution. For instance, there is a path from C to A, but there's no path from A to C. So that's a digraph and an adjacency matrix. Now, this is a bipartite graph. Bipartite in the sense that it has two parts. On the left is a list of people, on the right is a list of countries, and the lines join up where somebody has visited a country. So Angie has visited Senegal, Bev has visited Vietnam and Peru, and so on. So that's just introducing you to a new form of graph called the bipartite graph. Right, why are we talking about assignments here? We're talking about assigning people to jobs in countries in this case. So what we want is somebody to visit a country that they have visited before to make a film or something, make a presentation, find out some information. Now some people have to go to a certain country because they've only been to one. So Angie is only connected to Senegal, so must visit this country, which then has implications because if Angie visits Senegal, then Dorian will have to go somewhere else. That's the black dotted line is his visit to Senegal. It's not going to count. So one by one, you can find out by process of elimination who is going to go where. First of all, you colour in Angie to Senegal because she's the only person who's been to one place. You then remove one of Dorian's trips, which means that he has to go to Myanmar. That means that Evelyn can't go to Myanmar, so Evelyn will have to go to Vietnam, and so on. And you finish up with people being assigned to countries. So that's assignments. Supposing you had a situation where you had what you might call a complete bipartite graph. Every presenter has been to every country. Well, then how do you decide who's going to go where? What you do is you decide on the basis of the different costs. Presenter 1 might cost a lot less going to country 1 than presenter 4 for some reason. So what you do, you take the weight of the connection, the cost, we call it the weighted graph or the digraph. You take the information from the matrix of the costs, the adjacency matrix that you've produced for the costs, and work out who's going to go where. And that's going to use something called the Hungarian algorithm. Alright, let's move to a set of data that's a bit different. It's only 4 employees this time, Wendy, Xenophon, Yolanda and Zelda, and they're going to go to countries A, B, C, D, or do task A, B, C, D. The numbers, we don't know whether the numbers are miles, dollars, thousands of dollars, hours, could be anything. Doesn't matter, works for any of those. one way to approach the problem might be to say, okay, well, Wendy is cheapest going to A, so why don't we send her to A? Xenophon is cheapest going to B, let's send Xenophon to B. Yolanda therefore should go to D, which means that Zelda should go to C. The only trouble is, Zelda going to C is going to cost 50, whereas Zelda could cost 20 only going to A. So you could muck about. Let's say we send Zelda to A after all, which means Wendy will have to go down to C, which may not be the best because Wendy's C is 50. So you can see that there are issues with doing that. That's what I've called trial and error. Now the Hungarian method, which you don't have to read this down here, is just explaining why it's called Hungarian, because it was designed originally by two Hungarian mathematicians, uses a complicated but relatively foolproof procedure. And this is the procedure that you're going to have to follow. This is the procedure. On the left is our table of costs. Now, on each row you find the lowest cost, in which case Wendy is 30, and you subtract 30 from all of Wendy's numbers. So 30, 40, 50, 60 becomes 0, 10, 20, 30. Do the same for Xenophon. The smallest number is 30. Xenophon is now 40, 10, 10, 40, and so on. So first step of the Hungarian algorithm, to reduce each item in each row by the smallest value in that row. That is the note that you should take for the first step. Subtract the lowest value in each row from every value in that row. Now remember that table on the right has now gone to the left. This is where we got to after step 1. You now go through this process of crossing out the zeros using as few lines as possible. If you draw a vertical line down through column A, that gets rid of 2 of them. Doesn't matter what you do, you can do it with 3 lines. You could go down A, you could go down B, you could go down D, and you go long Xenophon, and that will get rid of all of them. Question is, do you need 4 lines? Why 4? Because we have 4 employees and 4 tasks. Do you need 4 lines? No, we did it with 3. Remember that table on the left? We're going to continue and do something else with it. This time we look at it column by column. Are there any columns with so far no zeros? Well, column C has got no zeros in it at the moment. Smallest value in column C is 10. So we take, in this case, 10 from each entry in column C. So column C goes from 20, 10, 30, 30 to 10, 0, 20, 20. Now, the question is going to be again, can you get rid of the zeros with less than 4 lines? Before I show you, let's have a think about it. You could go down column A, you go along Xenophon, and you could go down column D, and you're afraid you've got rid of all your zeros with less than 4 lines, so the answer is still no. I did not need 4 lines, and that's one way of crossing them out. No, we didn't need 4 lines, so we need to move on. Now you leave the lines on the diagram, and we look at all the uncovered values. In other words, not crossed out, and the smallest number that's not yet crossed out is a 10. We use that 10 and we add it to any value that is covered twice. So Xenophon has got 2 lines through A and 2 lines through D, so Xenophon goes from 40, 0, 0, 40 to 50, 0, 0, 50. We also take 10 from every number that is not yet covered. So we do 2 things at this step. We look at all the numbers which have not been crossed out or been crossed out twice. Wendy now, 0, 0, 0, 30. Make sure you can see why the numbers are as they are. Anything that's got a single line through it stays there. Anything with 2 lines through goes up by 10, everything else goes down by 10. We now have enough information to create a bipartite graph. Just use the values in the table which are 0. Wendy's got 3 zeros, so Wendy could do A, B or C. Xenophon could do B or C, and those lines have been drawn in there. Yolanda can only do D, and Zelda can only do A. Now we still haven't finished, but what you do, as it says at the bottom here, is draw a directed bipartite graph with an edge for every 0 value in the table. You'll see how this pans out in a moment. Obviously, we still have to make some decisions. Now we know that Zelda has to go to A, so that's gone in red. We know that Yolanda has to go to D, that's in red, which leaves B and C to be assigned. While Wendy can go A, B, C, it doesn't matter what at this stage. Wendy goes to B and Xenophon goes to C. Could be the other way around, but that makes more sense. So the red line is the final assignment. One more thing to do, go back to the original table and get those costs. What was the cost of Wendy going to B is 40. Zelda going to A was 20, we've used that one. Xenophon going to C is 40 and Yolanda going to D is 30. The cost, therefore, of the assignment, or the minimum cost, is going to be 40 plus 40 plus 30 plus 20, which is 130. And that is an application of the Hungarian algorithm. Well, that will be something for you to do in the exercise. I will approach the exercise in a separate recording.